Hello everyone, good morning. My name is Hiren Rupchandani, an Insaid data science researcher, and I welcome you to today's industry talk with Mr. Sameep Mehta. So, hello Sameep, good morning. How are you doing?
Okay, sorry. Hello, Hiren. Can you
Yeah,
hear me now?
yeah, as
Hey,
always.
good morning. Good morning. Good morning. Thanks for
So,
inviting me.
yeah, we are glad to have you here today. So, I'll give you an introduction to the audience, and we can begin with the session. So, Sameep is a distinguished engineer at IBM Research AI. His research interests broadly lie in AI, trusted AI, data quality, data preparation, data modernization, and metadata management. He is responsible for setting and executing data strategy at IBM Research. He is also adjunct faculty at IIIT Delhi in AI and data management, and he also regularly publishes at top AI conferences and has many best paper awards and also the best runner-up paper awards. So today Sameep will be talking about data quality in AI. We all know that data basically lays the foundation for many machine learning models, and it is very important to tune our data according to the model's needs. So what are the various researches that are being undertaken to improve data quality, for how data understanding is being improved, data quality management, data cleaning and preparation, etc. So some people will be talking about all of them. So hi again Sameep, and I will let you continue the session. Over to you.
All right. Thank you. Thank you, Hiren. And good morning, everyone. And thanks for joining today on Sunday. So let's get started. So I'm going to start sharing my screen. Hmm. All right. I hope you can see my screen in full screen mode.
Yeah.
All right. Thank you. All right, folks. So today, what we're going to talk about is really around the data side of our AI life cycle. So, so as Hiren said, right, data is one of the most critical part in making sure that the models we are building are of high quality, highly accurate, right, bias free, and one of the ways to do it is to make sure that our data is of good quality. So that's the purpose of this talk, that what is a systematic way we can get our data ready for AI. And we'll go over multiple kind of new issues in the data, which are only relevant for AI. How do we solve it? And then in the end, I will tell you how some of you could use these toolkits and APIs from IBM Research in a trial mode. So let's get started. All right. So all of us, right? I think just I think by show of hands or something, right? Like I assume, right? All of you would have built some kind of models, either in your classroom, job, internships, and or for just learning purposes. So we know that when we build a model, we have to spend a lot of time on the data side, right? And it starts from collecting or finding the right data. It starts from assigning labels to the data, finding missing values in the data, finding outliers in the data, and so on and so forth. And sometimes it's just like normalization, right? So that all the dates are same, the timestamps are correct, and so on and so forth. So at some broad estimate, right, that around 80% of our time is actually spent in data collection, data cleaning, making sure the data is ready for the next stage. So, but at the same time, this is not a fun activity, right? I think all of us know, right? Model training is a fun activity because you get to try with multiple architectures and see the results. But data is kind of manual process. It's a boring process. It's most time consuming. It's very nitty gritty, detail oriented. So it's not a fun process. So I think you see combine these two things together, that 80% of our time is actually spent in data cleaning, which is not a fun activity on very time consuming manual exercise. So that's where we want to focus today, to say that how do we make this process a little bit more scalable, more efficient, and so on and so forth. All right. Now I think the picture on the right side, right? Garbage in, garbage out, right? This is right. I guess all of us would have right heard this term in the first computer science class we take. That if you provide bad data to the system, be it a analytical system, be it a ML system, we are only going to get a bad model out. So nothing surprising here. Now, if you look at how the research community and industry community is moving, then we have made a lot of progress in last few months, few years to build automated system to learn AI models. Right? So Auto AI, Cloud Auto ML, there are open source toolkits which will take your data and build a good model for you. However, we know that the quality of the model cannot be good if the data is not good. So, and at least right in our research, our right prior art search, we didn't find too many toolkits and a systematic effort which right aims to measure the quality of the data and improve it. And that's where we want to focus. Now, just to give a little bit more numbers, right? I think for that 80%, right? So this was the picture on your left hand is really around from Kaggle data. So someone has done this survey from right, Kaggle. And if you look at the most time consuming exercises are gathering data, cleaning data, visualizing data, right? If you actually stack the first three on top of each other, they're going to be like really high. And almost right, I think double or triple the model building exercise. So this one again, right, not just kind of just tries to put some more color or put some more evidence to the 80% number which we saw. So what do we want to do, right? So what we want to do is we want to automate AI. We want to automate all parts of AI. And we want to use AI to automate AI. Okay. So I'm just going to, so there are like 4 parts of automation of AI, right? So first is AI preparing for AI, which is what we are going to talk about to say that how do we use AI to prepare our data for AI. Once we have done that, then comes AI designing AI. So this is really around your auto AI systems, which takes in the data and design your architecture, right? Learn your hyperparameters and all those things. Then you have AI optimizing for AI to say that, okay, once we have built the model, how do we improve the model? And finally, you have AI correcting AI, which means that what if your model is unfair? What if your model starts to drift over time? How can we use right AI to correct the model itself? So again, right, we are not going to cover all 4 of this. We are going to cover only the first part, AI preparing for AI. But I just wanted to give you a kind of a lay of the land to say that this is how the community is thinking about AI. Building AI systems to improve multiple aspects of AI and data and AI lifecycle. So it's just, I think we have made a lot of progress on AI designing AI, AI correcting AI, but AI preparing AI is something which we are really started on. All right. If there are any questions, I can stop for a minute and see if there are questions. Otherwise, we can go on. All right, we'll get started. Okay, so now let's look at a standard AI lifecycle. So what you see on your screen on the left-hand side is what you will get if you take any popular search engine and try for AI lifecycle. You will get this very nice, circular and almost right sequential pipeline where you start from data exploration, go all the way up to feature engineering, build the model, deploy the model, and you are done. But unfortunately, this doesn't work very well in real life. In real life, I think what you see is on your right hand side is what I think usually happens, where a lot of these stages cross cut, right? People, you will jump to okay, I see a question. I think and I read that question. I think that's slightly off topic, so I think maybe we'll take it at the end. Thank you. And where was it? Yeah. So I think this life cycle almost becomes a very, very interconnected thing. It's not a sequential thing in real life. And that's where I think it makes it very difficult, because now what you have is you have like different people doing different tasks and different people talking to each other. That's why we need a more toolkit based approach so that this process can be streamlined. Okay, so now I think again that I think if you were to take one thing out of what we have talked so far, I think just remember this picture. So this is a famous picture from Aisha, hand drawing hand, and this is what our hypothesis, our right kind of direction is, that we want to use AI to build better AIs. So just remember this picture, right? This picture kind of conceptualizes it very nicely, at least for me, that we are using AI for AI. All right. Now I think what we'll do. I think we'll go over some of the different aspects of noise or data issues, and then we'll come to the toolkit part. Now, one of the things is that if you have used, if you have built models or you played around with data at any point of time, there are a few tasks you always do on the data. Right? So what we do, right? We open the data most likely in Excel or in some kind of text editor, and start to see if the columns are normalized, which means all the column values follow the same pattern. Right? We figure out that if there are missing values in the data, we want to correct it. We want to see if there are some rows which look wrong or which are outliers. We try to remove it. So all these metrics like noisy data, missing value, they are needed, but they are not enough for AI. And that's what we are going to talk about, some of the new type of metrics which we need to consider. So for example, right, let's look at this example, this slide. So labels, right? I think if you want to do any kind of classification task, we know that classification task is simple, that you have a set of feature vector, you have a label, and you want to learn the decision boundary which separates two or multiple label classes, right? Simple definition. Now think about a case where your labels are wrong. If your labels are wrong, then you can only do two things. Either you can build a model which will be not so good because it will always get confused, or you can build a model which is very, very complex, right? Complex to the extent that it actually overfits the data. Both the conditions are wrong. We don't want to get into either of those conditions. So let's look at some of the examples, right? The first example, right? This is from Google Quick Draw dataset. Now, I think, if you look at this picture there, anyone can tell it's an elephant, but the given label is actually mosquito, right? So now think about it, right? If you have a lot of such errors, then it's going to be really difficult for a model to differentiate between an elephant and a mosquito. Because now some elephants are labeled as mosquito and maybe some mosquitoes are labeled as elephants. It's just very, very confusing now. Similarly, this is the popular MNIST dataset. Now, this is the digit. I think we can see it's a 3, but the given label is 5. Now, especially for this, I think I give a little bit benefit of doubt, because you can see why to some people it could look like a 5 also. It's close to, right? I think at least the lower part is very, very close to 5. But still, right, it's a wrong label, which is going to make the task of differentiating between 3 and 5 very difficult. So another example. Third example, right? Look at the text data, right? So you read this line, right? It says that I have had this over a year and it works very well. I'm very happy with this purchase. So this is the text of the review. If you read this text, it's a 5-star rating, but the label which was given is 1-star review. So now you can see, right, like how these kind of samples are very difficult to handle. And if you again look at some of the prior art, it seems that ImageNet has at least 100,000 such issues. So unless we resolve these issues, it's going to be very difficult to build a good model. However, as we know, right, resolving it manually is going to be a uphill task. We can't look at every sample, every label, and figure out, right, this thing. So we need an automated way. So this is again, right, some examples, some more empirical studies which says that okay, once you start to increase the label noise, how does the classification accuracy actually increases, right? So I think this is the test error. So as you corrupt more and more labels, your right, not surprisingly, your error rate actually goes up. Right. So again, that I think one of the things which I also wanted to cover is that many of you would be wondering, oh, why are the labels wrong? So think about this, right? Where are these labels coming from? So these labels come from 2 or 3 places, right? One is you take this label, take the data, and go to some kind of like crowdsourcing platform like Mechanical Turk or Figure 8, and say that, okay, right, I'm going to ask people to label it. And so some of the labeling error could creep in there because, like I said, right, someone right kind of quickly looked at this picture of 3 and thought it's 5 and labeled 5. So I think it's a manual error which creeps in. The other thing is nowadays there are automated systems to start labeling, and these systems will induce their own errors. And sometimes it's just right, the observation is wrong, so you introduce these label errors. So there are multiple ways that this label errors will come in, and sometimes it's easy to kind of look at the sample and say that, okay, this is not an elephant. Oh, sorry, this is not a mosquito. This is an elephant. I'm going to change it. But sometimes, in at least in the business setting, these wrong labels are also very, very subjective. You can't actually differentiate so easily. So, for example, right, if you are in, let's say, looking at some data for banking, it's very difficult to figure out, which is a banking data versus which is a insurance data, and then furthermore. So I think this is a tough task to solve, but nevertheless needs to be solved. Otherwise, the models are not going to be good. All right. So let's move on. Now let's look at. I'm going to stop here for a minute. See if there are questions on label noise or anything so far. All right. So we can get started. Okay. Now again, the other part is, let's say, a different metric we'll look at is data homogeneity, which means is all the data following the same pattern. So for example, if you look at, these are some of the real data sets, right? I think which have been a little bit more cleaned up, and which are, right, I'm not revealing the sources here because some of these are internal data sets, but still, right? So if you look at this, right, this is your customer ID, and in between customer ID you have these right phone numbers, and sometimes this phone number @ fax.in. So why do they come in? Because if you look at a customer ID, right? So you could have like multiple different data sets, databases which someone has merged, and while merging, they have done some misalignment or something like that. And similarly, then you have dates, right? So all the dates are correct in their own rights, but if you kind of start to build a model out of it, it's going to be really complex because now some different dates have different format. And this is like, I think I'll tell you, right, this is the most common problem. Either even if you're not doing AI, right, even if you're doing your reporting, dashboarding, analytical system, predictions, you open up any real data, I think this problem is going to creep in. So we want to solve this problem, right? And then again, right, I think look at another example, right? So this is our standard data set, and there is a column fair. Now, in the original data set, this column fair was tagged as string, right? Because it has the decimal and some numbers. So someone thought, okay, right, let's just flag it as string. So we just took this data set as it is and kind of ran it through our standard neural networks, SVM, right? Standard toolkits, right? No feature engineering, no extra data processing. And what we get is this accuracy, right? 68% and 61%. Right? Good enough. Then what we did was, all we did then is took this fair column and changed this fair column to float, right? Because this is actually a float number, right? We know. We just changed it to float. We did nothing else to any other part of the data. And you look at the accuracy jump, right? From 68% to 80%, 61 to 77%. So again, right, because we know, right, that how strings are handled versus how floats are handled are different. Floats are much easy to handle, at least in the classification setting, and that's what we got. So, and again, right, I think, some of these examples we have to, right, also understand some of these examples are exemplar, right? Not every time you are going to see the 10% jump in accuracy, but still, right, I think your model is going to be much more cleaner, much more simpler if some of these things are handled. And these are easy things to handle, right? You can actually do these things at schema level. It need not even do it at, right, like your data need not even change. You can do it at schema level. So again, right, so some of the things which do not matter so much for analytics, but I think they are going to matter, right, a lot for our AI and ML algorithms. Okay, now I think let's look at a third kind of data homogeneity. So it's a even simpler one, right? So what we did, we got some data from Kaggle, and there I think the gender column had multiple values, right? It has M, capital M, male, right? F, female, female, right? All kind of combination of male and female. Now, when you look at the data, open up the data and look at it, you understand, right? That, all the small m, caps m, male, they mean male, and the other one means female. But I think when you start to train a model, the model is going to treat them as 6 different values. And that's how it will try to learn the Michigan boundary. So we took that raw data set and the accuracy was 76%. And then what we did was we actually took the data set and asked some kind of human expert that, how these things should be mapped. Again, it's simple mapping, right? Everything which is male maps to M, everything female maps to F. And just by doing this thing, we got a 3% accuracy jump. So again, right, I think just one more example where right, when you open up the data, it will look all good, all kind of obvious, but then that's not how models are going to treat it. And I will tell you one more example, right? I think we recently worked on some data set where in one column there were 4 values, 0, 1, T, and F, right? And now we know, right, this is a binary column, we should only have 2 values, 0 and 1. But because this data set, this column was filled by 2 different applications, one application was using 0 and 1, other was using true and false. And now, but when you look at the column, it has 4 values, 0, 1, true, false, T and F. And more importantly, now it cannot be treated as a binary column. It has to be treated as a string column. And that's how the problem starts. So once you change it to 0, 1 binary column, suddenly you again, right, get to see a increase in accuracy. And one thing to note here is that a lot of these transformations are very simple transformations, right? We are not doing, right, some very advanced transformations which requires a lot of effort or GPU cycles or CPU cycles. These are very simple, right? That all the males map to F, all the females map to F. Right? Very obvious, very intuitive. But by doing these small things, it has an exponential impact on the final model performance. Okay, before I move forward, I'm going to stop for a minute and see if there are questions. Okay, at least, right, someone should just say yes or no so that I know that you are able to hear me. Hiren?
Yeah, we are able to hear you.
Oh, okay, all right.
Yeah.
But there was a lot of silence, right? Sometimes
okay.
It has happened that I got dropped from the call and kept talking for 15 minutes.
We are good.
All right, good. Yeah. All right. So now let's look at yet another aspect of data quality. So sometimes what happens is that you start to work with the data and you realize that the data is not enough. Now, and there's a difference, right? Like, let's take a step back, right? When we do our, let's say, right, BI reporting, right, where we have to make some pie charts or line graphs, there we assume that the more the data is, the better quality charts we could make, right? It's a valid argument there. But I think for AI, what happens is that, first of all, more data doesn't mean that you can get a better model, because the data could be of bad quality. So that's there. And the other thing which could happen is that you have a lot of data, but then there are these particular segments where the data is not good. So for example, right, you collected a lot of the data and you realize that you don't have good representation of, let's say, males in third tier city, or you don't have good representation for, right, let's say it, people with height greater than 6.5, right, feet in your, right, the health data, and so on and so forth. So you can always have these issues where the data is not good, and it's a very different kind of data quality which we don't, right, kind of see anywhere. But I think for AI, it's very, very useful. So again, right, so what we do is we have algorithms to now generate data. So primarily three use cases. One is you actually have less data, but you want to do, right, build models. So you generate more data so that now you can build models. The second problem, which I explained, the data is not good for some particular cross section of the population. So you focus there and you generate more data just for that particular segment. And the third one, which I think, a lot of us have faced, is that the real data cannot be shared with everyone. So we want to build models, we want to build realistic models, we want to build models which are going to be useful, but the data cannot be shared because it's confidential, maybe contain, right, sensitive information, personal information, so on and so forth. So to solve that problem, I think what we do is we generate data, right? We have our data synthesis algorithms. So how do these algorithms work? I think, don't worry about the code and all, but how it works is that, you take the data, you understand the data in the sense that you generate your distributions, you generate different constraints. So right, so you can generate that, okay, in my data, the age is between, right, 0 to 18. That's my data, which means that any data I generate, the age column the age should always be between 0 to 18. I don't want to generate age greater than 18 because that's what my original data is, right? You could, right, same thing for height, weight, whatever the other columns are. So you generate these, extract these rules, and then using these rules, we generate more data which satisfy these rules, right? So if you look at this, so on your right hand side, this is the original data, right, which was given to us, and on the left hand side is the synthetic data which has been generated. Now you can see that there, if you look at the data, you will see that, okay, there are two things, right? One is at the individual sample levels, there are differences, right? So for example, you see a lot of variations on your left hand side, but those variations are not there in the right hand side, which is fine because, we are, right, generating the data, then some of these things are going to be missed. But at the same time, if you look at a distribution level, the distributions are very well protected. And as we know, right, if you want to build our AI models, one thing we do is we, right, kind of learn from distributions. So, right, distributions are protected, but individual, right, variations may or may not be protected, which is fine for the task we have at hand. So this is yet another kind of very different way of looking at data quality, where your data is fine, but it is actually less. So we want to generate more and more data so that it can be, right, we can learn better models. Okay. All right. Now I think so. We talked about a lot of right, kind of different metrics which are useful. We talked about some examples why they are useful, what impact they have on our data quality, and so on and so forth. But now the question is that, how do we go about it? So what we have done at IBM Research is we have built a data quality toolkit. We call it data quality for AI. And the data quality toolkit has these kind of 4 different components. So the first one is data validators. So data validators, you could think about almost like data checks. So these are the functions which tells you if your data has label noise, if the data is homogeneous, if it has bias, so on and so forth. So it actually only profiles and tells you that, here are the issues with your data. But finding the issues is only, battle half won, because someone still needs to correct it. To help in correction, what we provide is we provide a set of remediators, which can help you, take the issues which the validators have found and actually fix those issues. Now, validator and remediators are good, but I think we also know that in many of the business scenarios, there are certain constraints, there are certain business rules which are almost like external to the system, right? They are in the head of right, business domain guides. So we have a method to incorporate those constraints. And finally, we have what we call the concept of pipeline. So you think about it, right? One data set could have multiple issues. And how do you solve it is by pulling together a pipeline, which is composed of different validators and remediators. And that's how you build the large pipeline. So validator remediators are almost, you can think about as atomic operators, which can then be combined to build a more advanced data quality pipeline. So this toolkit is available, and I will show you in a minute on how to use it. Now, I think we have talked a lot about this thing. Let's look at a small video, and I hope this video plays well on Zoom. Otherwise, we'll figure it out something. But let's look at a little bit of the video. Right? It does not have audio, just the video. So I'm going to stop and kind of play it. Right? Okay. Okay, so let's start. I think. Okay. Okay, I'm going to just. Okay, so we are reading a structured file in. So this is our data set which you're going to read in. And okay, I'm going to pause here for a minute and actually explain to you what's happening here. So we have read a file in, and we have computed different. We have applied different validators on the data. Now I think what you see on your left hand side are different validators like homogeneity, label purity, data fairness, data parity. Some of it we talked about already. And then what you see is the individual scores. So the scores is 0.5, 0.8, 0.7. And for data parity, it's a good data. You don't have to do anything. It's high quality, right? And overall data quality is simply average of these things. And you can find your own methods to find the overall quality. So that's our original data, original view of the data. Now remember, right? I think we don't want to clean the data just because we want to clean the data. We want to clean the data so that we could build better models. So what you see on the right hand side are accuracy of different model types like linear model, decision trees, and all those things on the original data, right? And you can see accuracy ranging from they are around 70%, right? 70%, 73%. So this is the baseline view of the data and the models which we can build on data. Now, of course, right, I think one could say that, I can do some more, I can spend more time on the modeling and improve this model. Definitely you could do that. But then, right, on the clean data, that advanced model is going to do even better, right? So let's move forward. Okay. So now what we do is we try to, say that, right, we are going to correct some of the data. And I think I'm going to skip some of these things. And by the way, I think one other thing to look is that your AI model may not only be measured by accuracy. So you could have different model indicators. So what we have just as an example, we have another indicator, which is fairness. So you look at the original data, and this is the fairness we get. And I think, we are doing fairly well on fairness. It's not an issue, right? Almost 90%, right? So on the fairness metric, our data might be okay, but on the accuracy side, we have some work to do. Okay. So now we start to correct the data. And remember, I think this is the example we already saw, the homogeneity found, and we are going to correct this data by finding different samples. And we already went over it. So I think I'm just going to move a little bit faster here in interest of time. Okay. And then you look here, right? I think so. We started on the homogeneity. We started with 0.5. We then transformed the data by using, kind of giving appropriate values to each cell. And now our homogeneity score has become 1. And as soon as it becomes 1, you could see how the performance of different model types have impacted, right? So, 5 out of 6, the performance have improved from 1%, 1.5%, 0.5%. And for one of the models, it is kind of it decreased a little bit, which could happen. Right? So again, I think you can go ahead and do it for everything. you can, right, we have built in, right, explainability so that, um, it's not just that we are cleaning the data, but we are also right, telling the user what we have cleaned, what was the before transformation, after transformation, how many rows, and it can go, right, you can go in any level of details you want, right? So, okay. I'm going to touch upon two more things and then we will open up for the questions. Now, one of the things you have to also think about is the following, that we have taken our original data and now we have started to apply our cleaning operators on it. Now, one of the important thing is not to do repeat and redundant work, right? Especially if you're working in large teams. So whatever data improvement someone has already done, we want to kind of record it somewhere so that other people don't have to do it. So towards that, I think what we are bringing out is what we call data readiness report. So data readiness report starts from baseline. So this is our baseline, right? So as soon as we read the data, we provide this kind of report which says that, okay, from a, let's say, outlier detection, your data has 11% outliers, right? 89% is okay, 11% outliers, right? So this report goes and, right, you can have like hundreds of such metrics which stores the baseline data. And then what you do is you start to update the data. And as you start to update the data, you form these kind of graphs, which says that, okay, user A had done the data profiling, and for feature relevance, he applied algorithm to improve the feature relevance. User B came in and that user worked on the data for user A and did some more data, right, kind of computations. At the same time, a user C actually thought that he is not interested in what user A and B have done. So he created a side version of the data and improved that data. Now you think about it, right? I think as soon as a new user comes, right, let's say user D, and he can look at this chart, this particular lineage graph, and say that, you know what, I think for my purpose, I need a data set which is free from outliers. So I am not going to do all this work all by myself. I'm going to start from where user C left, which is to do outlier removal. And I'm going to use the version which is created by user C, and so on and so forth, right? And you can see how this is powerful because now over time, right, the new data science team or the new user does not even have to do anything on data. He can look at this graph and say that, okay, I'm going to pick this version because this one fits my need. Or I think someone could say that, you know, whatever has been done earlier is good, but I have very different need. So I'm going to change the data on my own, and this graph gets updated to reflect that change. So this is really important because now you're saving lots and lots of time, and you're almost like building up the collective wisdom of a lot of people so that you don't have to do a lot of this work all by yourself. So this is what we call data readiness report. So again, just to recap, right? So it has the baseline metrics of where the data started from. And then it has the detailed view of who did what to the data and how did that operation improve the data quality. Okay. Now I think, you know, we talked a lot about, you know, the algorithms, the right, label noise, how do we correct it? So one of the things what we have done is if you go to developer.ibm.com/APIs, you would be able to see a tile like this, which says data quality for AI. And so these are APIs. So if you look at the APIs, right, it has like under structured data, it has things like class overlap, right, data duplicates, data homogeneity, label purity, a lot of these things we talked. So now they are available as APIs. So you can just sign up for the trial version, and you could start to use these APIs. And if you read this text, I think we also maintain a Slack group. You can join that Slack group and ask questions there, give your feedback, give your suggestions, all these things. Right? So a lot of these things are now available as APIs. You don't even have to write any code or install something. You can directly use these APIs and at least do the validator part. So what we have made public is the validators, not the remediators for now. But you know, so I would encourage anyone who is interested, use these APIs, see what you get, and right, give us feedback. And then we are going to keep adding to this list. So I think I had around 45 minutes. I think good on time here. So maybe, I'm going to stop here. And I know there are a lot of questions on the chat, which I could not see because I was presenting. We can go over this and maybe unmute. Maybe I think,
I'll
you guys can unmute and ask.
Yeah, I can read out some important questions that, to be honest, asked in the chat. So Prashant Gabhane has asked if AI could prepare AI, will the jobs employing data scientists will diminish? What do you think?
No, I don't see. I don't think so because you have to understand that I think there are few tasks which could be automated, and there are few tasks which will still need lot of human expertise, lot of human. So I think I would say that I think we are automating the tasks which are time consuming, but I think still right there is a lot of right domain information, tribal knowledge which needs to be accommodated. So and you think look at the job market, right? Do you say less AI jobs in market because there are systems like right auto AI, auto ML? I think it's the reverse because of these systems. Now AI is getting adopted at so many places, right? That you need people everywhere. I don't think jobs are going to diminish. It's actually going to increase only.
Yeah, makes sense. Similar okay, again from Prashant. So how is fairness estimated? Like this question was also asked by someone else. So wait, you talked about data fairness and debiasing. So how can that what are the measures that can be used to estimate that?
So I think that's a good question. And what I will do here is let me give me a minute, right? I think because I think instead of okay, and let me again share my screen for a minute. Okay, where's the share button?
I guess your screen share is enabled.
Yeah, I'm just give me 1 minute. I think something is. Okay. Okay. So I think what I would do is I think instead of kind of giving you one metric to kind of estimate the data fairness, what I would encourage you is to go to this website, right? AIF360. Right, mybluebricks.net. And what you can play around here is the AIF demo. And the second thing is, if you go to this GitHub, if you just, I think you don't have to write it down. You go to search engine and just type AIF360. So this is an open source toolkit from IBM, which has, I would say maybe around 50 different metrics to compute data and model fairness and how to validate it. And so there are some simple metrics like disparate impact, and then more complex metrics to debias the data and use sampling and do data debiasing, model debiasing, and so on and so forth. So I think that's what I would encourage you. And I think this AIF 360, this is very nice because now it actually has your exact kind of just point and click tutorial which you can use to check the bias and debias it. So I think just use this one. And if you still have questions, then feel free to email me.
Okay. So one question from Mr. Lalit Garg is, where can we explore the other parts of AI, like AI correcting AI? So
I think AI correcting AI, right? So I think so a lot of these things I would say are part of open source, and some of these things you can actually just sign up on the different services on IBM Cloud. At least, right? I'm aware of IBM Cloud. I'm sure other cloud provider will also have it and try it out. But again, a lot of these things are kind of part of bigger systems and not available as APIs. We are in process of making a lot of these things as available as APIs. We started from data quality APIs for now.
Okay. So
but I think I think, and just to complete that part, right? So one part, like let's say AI correcting for AI, right? One of the AI correction is that how do you, right, kind of correct your model so that they are, let's say, fair, right? And the toolkit I showed, AIF 360, it has those methods, right? Open source toolkit, Python code, you can use it. Similarly, you could have things like, okay, how do I make sure that my model is robust? There are toolkits for that. You can use those toolkits. How do I make sure that my model's explainability is correct? There are toolkits for those. So I think a lot of these, I wouldn't say that there is a single API which you can just call and correct your data or your model, but there are lots and lots open source material out there which you can definitely use.
Okay. So Mr. Sushil Thakur is asking, how can we be sure that our model accuracy level is at optimal level and it can't increase further? Is there any way to determine that?
Nah, I think it's a, you can't do that, right? Because there will always be, right? You can always come up with better models, better data to improve the accuracy. But I think one thing to, so there are a few things to think, right? So one is, you know, after a certain point of time, you will realize that the effort which you put to improve the model and the actual improvements you get, they are going to be, right, almost like inversely proportional. So you're going to be putting a lot of efforts, a lot of, right, GPU cycles, but the improvements are going to be very small. So, and the other thing is that you also want to make sure that your model is still generalized and it's not overfitted the data. So I think to answer, I don't think, at least that I'm not aware of any, right, rule of thumb which could say that, okay, now you can't improve your model further unless your model accuracy is 100%. You can always improve. But then I think you have to serially see that improvement, what it costs on generalization error and how much effort you have to put to get that extra, right, 0.5% or 0.25% accuracy. And right, I think, and that's where I think, the data scientist actually comes in to connect to previous question, right? Because a lot of these things after a while stops being a science, they start becoming an art. So you as a data scientist, model scientist, you would be able to figure out that, this is what it is. And any improvement after this is not going to justify the effort. So that's what I would say, right?
Okay, thank you. So last two questions that we should explore. So Miss Ashwini is asking in the Q&A. So you mentioned about user-defined constraints, but for different processes, data would go from hand to hand or one team to another. So do these constraints might change with different teams?
Yes.
Okay.
And I think, that's where this is precisely, I think, first of all, I think very good question. I think this is precisely the reason why we started to work on the data readiness report. Because now I think, as the data flows to different teams or, different people, and they apply their own constraints, I think all these things could be now kind of stored in this data readiness report so that people are aware of what constraints have already been applied and what needs to be done. So I think it's an excellent question. And I think in all real life settings, I will not even say most, in all real life settings, we have seen that the constraints, the business knowledge actually changes from team to team, and not just team to team. Sometimes it's like scenario to scenario. The same team, different scenario, they will have different constraints. And that's why I think, we want to capture a lot of these things in the data readiness report to make sure that life becomes simpler as we go and use the data multiple times. So excellent question. Completely agree.
Okay. So last question for the day. Godfrey is asking, if you are generating synthetic data when real data is not available, it may make a good score on tools like fairness, parity, homogeneity, etc. So how reliable is this data? Will it be reviewed by customers or stakeholders for correctness or relevance?
Yeah. No, great. Another great question, right? So there are a few things, right? One is that so again, let's look at two extreme cases, right? So one extreme case is that, I don't do any distribution based generation. I just say that, okay, I'm just going to randomly generate some data and hope that data is correct, right? And we know that that's not going to work out, right? So if you randomly generate data, it's going to be all bad. At the same time, I could just say that, okay, I'm going to fit like very, very tight constraints and generate almost like perfect data, like you said, right? Which does not have homogeneous, right, errors and other things, right? So that's fine. But then there is a middle path, right, where you say that, okay, I'm going to take my constraints and relax the constraints a little bit, and then generate the data. So for example, right, let's look at the example we had from age, right, 0 to 18. So this particular constraint, right, 0 to 18, someone could just say that, you know what, 0 to 18 is a good constraint, but many times we actually see data entry error because of which the age is entered wrong. And now what I can do is that I can relax that constraint a little bit to say that, you know, for every, 100 samples you generate, 2 of those samples may not actually follow this rule. In which case, a lot of these realistic data issues could also be incorporated into the data generation mechanisms. And other business KPIs could also be entered like that. So I think very valid question, but I think that's at least right from our side. That's how we are trying to handle it. To say that okay, that you take these constraints, right? Work with a business user, ask him if these constraints are correct, if he wants to relax certain constraints, and then use those relaxed constraints to generate data. But of course, right? I think the synthetic data is still going to be synthetic. It's not going to be real data. So some of the discrepancies between real data and synthetic data would always be there, right? We can't get away with that fact. I hope I answered that question.
Yeah. So thank you, Sameep. It was actually a very great session, and I guess we should end the session now. So it meant a lot for us to have you here today, and I guess a lot of learning was there regarding how data actually molds our models. So thank you again for joining us. And I would also like everyone else to thank Sameep as well for giving the wonderful presentation and insights. Okay. So
thank you.
Yeah.
Yeah, thank you, Hiren, for inviting me, and thank you everyone for joining. And I think like I said, right, Hiren has my email address. It was also on the right slide. I think if you have any further questions, have difficulty in using the APIs, feel free to contact me. I think this is a extremely important area of research and almost like a upcoming area where very few people are working. So if any one of you is interested in working on these problems, working with us, I think please feel free to drop me a note.
Okay. So if anyone has any queries, you can connect with Sameep on LinkedIn, or you can have his email address, which was in the slides. Okay. So thank you also everyone. Thank you for joining us today and making this session better. We will be stopping here for today, and you can also share your link to the friends who might be interested. So have a good Sunday. Have a good
Thank
Sunday,
you.
Sameep.
Bye.
Yeah. Bye.
Bye.